Okay. Shall we talk about some linear approximation?
Yes.
Okay. So we left off with number 5. No idea what 5 was. Hooray for number 6. Number 6. Find the linear approximation to g of x at x equals 8. Then we're going to use that linear approximation to approximate the value of the cube root of 10 and the cube root of 16. Compare the approximate values to the exact values. Find the error of your approximations. So I don't know, did they just ask us to do like 5 different things here? Let's start by finding the linear approximation. Do you remember what you're doing? You probably didn't start the homework last night and you've slept since then, right?
Yeah.
But linear approximation, basically you're finding the tangent line, right? In this case, it's the tangent line at x equals 8. So I don't know where you guys want to start.
I think that was over there.
I really thought I heard a knock on the door. So
I heard it too.
okay, so I wrote g of x, but really I really need to find is g of what, 8? So if we find g of 8, that is the cube root of 8, which is 2. So I know I'm going to have the ordered pair 8, 2. Derivative, and I don't know what order you guys are doing this in, we just know it all needs done, right? Derivative, what do you know about the cube root of x? That's
X to 1/3.
x to the 1/3, so the derivative is 1/3 x to the negative 2/3. If I rewrite it in a different form, it's 1 over 3 x to the 2/3, which we could say cube root of x squared if you want. Technically, is this technically a non-calculator problem?
I think, yeah. Yeah, but the front ones were too.
Well, I know. No, last page were calculators, 3, 4, 5. I almost feel like this could be a calculator though too. Because we're dealing with so many of the decimals and everything. I think the calculators are going to work a little bit better. Okay. G prime of 8. So I'm going to do 1 over 3 times the cube root of 8 squared. Just a little friendly basic math reminder. You can do the cube root or the square first, right? My brain's going to do the cube root of 8 first, which takes me down to 2. And then 2 squared is 4. And then 3 times 4 is going to be 1/12. So if I write my linear approximation, L of x, 1/12 times x minus 8 plus 2. Sound good? Okay, so find the linear approximation. Okay, check. Use the linear approximation to approximate the value of the cube root of 10 and cube root of 16. So it's asking us for cube root of 10 and cube root of 16. Basically, we need to use our linear approximation formula when x is 10 and when x is 16. Okay? Because the given function was cube root of x. So we're going to find for x equals 10. So if we're trying to find the linear approximation, we're going to put that into our formula, right? So this is, I guess, officially g of x. Well, nope. G of 10 is approximately equal to L of 10, which is 1/12 times 10 minus 8 plus 2. So G of 10 is approximately L of 10. 10 minus 8 is 2. 2 times the 12th is 2/12, 1/6. My brain says 2 and 1/6. It's probably not what I should really put, because we don't usually use 2 and 1/6. 2 and 1/6 is really 13/6, yes? Or maybe I'll put them both there. sorry, changing my minds. We also want to repeat the process and for x equals 16. So g of 16 is approximately equal to L of 16. 1/12 times 16 minus 8 plus 2.
So why do this have cube root?
Say what?
Why do this have cube root but not?
Because, so the given function was cube root of x. And so when we write this linear approximation is for the cube root of x. And so if they want us to find the approximation of cube root of 10, it's the cube root of x when x is 10. The cube root of 16 when x is 16. Does that make sense there? Okay. Let's see. 16 minus 8 is 8. 8/12 is 2/3 plus 2. So my brain says 2 2/3, which is 8/3. And as I look at my notes on both of those, I have decimal equivalencies written down because that's what's going to make our next section easier. So 2 2/3 we know as 2.6 repeating. 13/6 is 2 1/6, so that's 2.1666, right? And actually, if you compare those, that makes it, yeah. Okay, so we use the linear approximation to approximate the value of the cube root of 10, the cube root of 16. Notice we're all in the ballpark, right? Cube root of 8 was 2. Cube root of 10 is approximated to be 2.166. Cube root of 16 is approximated to be 2.66. Now, it asks us to find the error, right? Compare the approximate values to the exact values. Find the error of your approximations. So basically for both of these, so if we talk about 10, in order to do the error, you're going to do the exact g of 10 minus the linear approximation at 10. This is where you have to grab the calculator, right? Because I don't know the cube root of 10 off the top of my head. I can tell you what I have written down the cube root of 10 minus our linear approximation of 10 is, but I don't have. So if I do the cube root of 10 minus, whoops. Cube root of 10 is 2.1544, so on and so forth, minus that 2.166, or in other words, minus 13/6. Negative 0.01223, so on and so forth. My notes. Why? Okay, what did I do wrong? Did you guys get the same thing, or did you?
0.122231976.
Okay. I'm going with I probably have something written down in my notes wrong. in my notes, I have 0.01216, which isn't too far off, but...
Is it for the 16? Or are you looking at the wrong one?
Nope.
That's what I got.
What, the 0.01216? Or you got what I have on the screen?
I got the 216.
How'd you get it?
I did the cube root of 10 minus 2.1666.
Did you use the, oh, you know what, I just thought of something. No. Did you round them or something? I'm confused. Why am I so confused about this? I don't know.
Did you do minus?
I guess the
13
more
over
sixes
6?
you subtract,
Yeah,
That's what-
the closer it gets to that.
Yeah.
Okay. Okay.
I added 3 more 6s on the end and I got that.
Okay. So maybe I have a rounded answer written down here. I don't know what Now, for error for this one. What is this? Our error is going to be less than 10 to the
-1.
negative first because there is 1 decimal of 0 place. Okay. We also need to do this for 16. You know, and I wrote, I guess I really shouldn't have had a minus there if I said it was the absolute value of it. Cube root of 16. 2.5198421 minus the 2.666, so on and so forth. And if we do the absolute value, it's going to be 0.1468, so on and so forth. And what kind of error does that give me? Less than 10 to the 0.
Is it something to 0?
It is, but based on what we're talking about error, we're going to leave it in this form. I mean, I agree. I thought about that too. I was like, no, because when we talk about error, it's always 10 to some power. So
I was also just double checking.
It is. Okay. I do agree with that math fact, if that's what you're wanting. Confirmation of anything to 0 is 1. Yes, I will confirm that.
So 10 to the 0, is that like a really good error? You want your error to be like 0, like 10 to the 0? Is that
I
like?
think you want it to be a release.
I think you want it to be like
Right.
Because that means you're really close to that.
Because here, like this one is 10 to negative 1, we're a little bit closer because it's 2.1, 2.1, and then it's off when you get to the second decimal place. Whereas here, they are off at the first decimal place. So 10 to the 0 is kind of the worst error you could
Okay,
have.
so the more negative it is.
Right.
Okay.
Because the more zeros in your decimal
Yeah,
is a good thing.
Yeah, I didn't.
Because that means it's closer to a more accurate answer. Okay? No, good question. Okay, 7. Let f be a function that is differentiable for all real numbers. The table. You guys have missed tables, right?
Yeah.
No? Okay. The table below gives the values of f and its derivative for selected values from -1 to +1. The function is concave up in this closed interval. Somewhere that's going to mean something, right? We don't even know what we're doing yet, but somewhere that's going to be important. Okay, A. Write an equation of the line tangent to the graph of f of x where x equals -6/10. You have all the information you need right there? We're going to write our linear approximation. F of x is approximately equal to L of x, which is, what's my slope? -2. X minus -6/10, so x plus 6/10 minus 51. Use this line to approximate the value of -5/10. That's easy enough, right? So notice it does say approximate. finding f of negative 5/10, which is going to be approximately equal to L of negative 5/10. Negative 2 times negative 5/10 plus 6/10 minus 51. Negative 5/10 plus 6/10 is 1/10. Negative 2 times 1/10 is going to be negative 2/10 minus 51. My mental math says negative 51.2. So my linear approximation is negative 51.2, or an approximate value of f is negative 51.2. Okay. Is this approximation greater or less than the actual value of f of negative 5/10, and give a reason?
It's not good enough, so the define's gonna be below it.
It's going to be what?
Below it.
Does that make sense? You visualize, and I tried to write points in my work, but there's a concave up graph, right? I mean, I can draw this a bunch of different ways, but if I draw a concave up graph, any tangent line is going to be where? Well, that's not a tangent line, that was a secant line. Any tangent line is going to be below it, yes? And so those y values on the tangent line are going to be below the actual values. So this is what you would call an underestimate. It doesn't actually use that wording there, does it? Okay, so I'm going to write a few words here. Since f of x is known to be concave up on the interval negative 1 to 1, the tangent line lies below the curve, so the approximation is less than the actual value. And my example here is if the curve is my function, so if this value is f of negative 5/10, then the linear approximation is going to end up being directly below it because the tangent line is below it. Okay? Because you're always, if we're talking about negative 5/10, those are going to be on the same vertical line. And again, yes, you have heard the word underestimate. Okay, next. write the linear approximation equation for f of x at x equals -1 and find an approximation for -1.2. So, I guess I'm just going to write my linear approximation under A because I got to do that first. Let's see, we're doing this. Actually, you know what? I think I'm going to do this part over here, and that way my -1.2 is right under there. So we need to know f of -1, right? F of -1 is going to be 1 over -1 minus 1, so -1/2. And then derivative. Which way do you guys want to think of the derivative here? If we think of this, I'm going to go with the idea of this is x minus 1 raised to the negative first power. Then I'm just using the power rule, right, to take the derivative. I don't have to use the quotient rule. So negative times x minus 1 to the negative second. Officially, I should say times the derivative of the inside, but the derivative of the inside is just 1. Derivative of x minus 1 is just 1. If I rewrite this in a little bit neater form, it's -1 over x minus 1 squared. So then the derivative at -1 is -1 over -1 minus 1, quantity squared. -1/4. My math matching up? It is. Okay. So can we write our linear approximation? I'm going to go ahead and I'll put that over here. F of x is approximately equal to my linear approximation, which is, where's my slope? -1/4 times x minus -1, so x plus 1 minus 1/2. Stop me if I go astray. Definitely gone astray today, so. So if we actually get to A now, which says find an approximation for -1.2, you guys know what to do, right? Plug it in. So I don't know. I almost feel like should I go to decimals? It's whatever. -0.25 times -1.2 plus 1 minus 0.5. -0.25 times -0.2. Work it all out. I think that's what I have. So if you did it yourselves, it was -4/500, right? Or that would be 9/20 if you went the fraction route, -9/20. Calculate the error of approximation. How are we doing the error? Error. That is the exact minus approximate, right? So when I do, whoops, exact minus approximate, that's doing the actual f of -1.2 minus the linear approximation of -1.2. Okay, however you want to remember it. Exact is negative 4.454545 repeating minus the negative 4500ths. And so I end up with 0.0045, I believe. Yeah. So what do we know about our error? It's less than 100th. Okay. 9. Okay, notice the calculator. Given the implicit curve, write the linear approximation of the tangent line. So, obviously one of the things we need to do is find the derivative, yes. Which in order to find the derivative, it was an implicit curve, so we could use implicit differentiation. That's what I've done on my notes. I'm trying to figure out where... Okay. I was trying to figure out where I got the actual point from. I didn't use the equation to find the point. What did I use to find the point? They gave it to us on the picture, right? Sorry, I was staring at my notes saying, why do I not have work of me finding the point? Like, I don't see it. So, okay. Now, before we implicit differentiation here. Last year, before I looked at the way she does her notes, I would have, okay, derivative of 2x, derivative of natural log of this, and then I would have had to multiply by the quotient rule. However, what I like better before we derive is x squared plus, how can you break up a natural log of a quotient? This is the natural log of x minus the natural log of y. Look for that. I'm right there with you. I've got to learn to look for it too, because right here I can do the natural log or derivative of natural log of x, derivative of natural log of y. That, in my opinion, is going to be a lot easier than having to do, okay, the derivative of the natural log of something times the derivative of something, where then I have to do the derivative of x over y. So then I'm doing the derivative of a quotient rule. You're getting a little messier there. Okay? So, what is the derivative of x squared? 2x plus derivative of natural log of x. 1 over x minus derivative of natural log of y
1 over
times dy dx, because we're doing this implicitly, equals derivative of 1, 0. Okay? That was a lot easier than having to do chain rule and all that with that natural log. Okay, so we need to solve this for dy dx, right? How much of this can you guys do in your heads? Huh? I'm going to run out of room real quick here. I'm writing kind of big.
You're going
to subtract these two terms over, yes?
I can do that in less than.
Actually, you know what? I'm going to add the dy dx term over to the right, because otherwise I'm going to have everything being negative, which is annoying. So I'm just going to add 1 over y dy dx. So I'm going to say 2x plus 1 over x is going to be 1 over y dy dx. Now, if I really want to, I would have flipped it right then and there, but I didn't. But if I flip it now, dy dx, how do I get rid of 1 divided by y? Multiply by y. So I'm going to write this as y times 2x plus 1 over x. That's a fun derivative, huh? What do we need to know about this derivative? Yeah, so we need to know the derivative when x is 1 and y is 1.
Why?
Seriously, Mr. Fly?
No shot the fly did all that.
He did.
He landed on the arrow because when I looked down, he was, see? Look, there's 4 little dots there too. That was wrong. These flies. Okay, it needs to get cold outside at this point then. The flies are killing me here.
The flies are intended for us.
They're attracted to me. I don't know.
Must be that. Must be
In
that.
physics,
They follow here, which you can.
No, there's flies all the time in my classroom. So unless you're hiding out in my classroom all day.
There's flies all the time in oxygen. I remember softball, you just walk around, you find a dead fly on the gym floor. It's like,
It is not uncommon for me to come in the morning and have to clear dead flies off the ledge back there.
I remember
Mr.
that.
Kevin
I used
Megan Nuggets for first.
he did.
For flies?
Yes. I do.
Oh my goodness. She's got a foot on her second.
Oh boy.
It's been a day, I think.
It has been a day, let me tell you. Okay. Derivative evaluate at 1. I quit, man. It's going to be
You can't quit till next year.
3. Okay. We write this linear approximation. So, they didn't tell us, is it F, is it G? They didn't tell us that, did it? So, I'm just going to say f of x is approximately equal to L of x, which is a derivative of 3 times x minus 1 plus 1. Okay. Now, because this will be helpful later, okay, before I go any farther, they gave us an implicit curve. Okay, remember implicit is when your x's and y's are mixed up and it's not explicitly solved to make y equals. I'm going to take a moment and take this equation here and solve it and make it y equals, because it will be helpful to know it's either down in part B and or C. Okay? And it's good skills. Now, we already have x squared plus ln x, ln of x over y equals 1, and then we went here, yes? I'm going to use that line. Okay? If I want to get the y by itself, how do you guys feel if I say I'm going to add natural log of y to the right, subtract 1 back to the left? Does that make sense? And so then if I write this out, I'm going to flip-flop sides. I'm going to say I have natural log of y equals x squared plus ln x minus 1. Do you remember how to make this y equals? Because we can go straight to y equals now.
Do
Does it have something to do with E?
Uh-huh.
raise the other side the E?
Okay, and there's 2 different ways we can talk. There's a couple different ways we can talk about this. We know natural log is base E. That's given, right? Now, Ethan mentioned it would be raising both sides to E is what it would be doing. It'd be making this, or e to the natural log of e to the y, and e to the x squared plus ln x minus 1. And I'll demonstrate that here in a moment. My thought was more of a, remember the phrase left, right, middle? How do you get out of exponential form into regular form? Or log form into exponential form? This is log, so it's the base is your left, the right is what it equals, the middle is what's right here. So that's going to be e to the x squared plus ln x minus 1 equals y. And then we have a y equals. Now what Ethan was showing, what Ethan was talking about, is he said, okay, it's going to be e to the natural log of y equals e to the x squared plus ln x minus 1. And how does that help me? Yeah, when you have base e and natural log has a base e, remember there's a log rule that says if the numbers in the spots of the e's match up, it's just equal to whatever's in the log. And so this becomes y equals e to the x squared plus natural log of x minus 1. Okay, this right here, it's just our explicit form. It's a good skill to have. It's going to help us here in our next piece. I think it's the next piece, yeah. Yes?
So it's, go on, I just need to figure out the work part now. If I don't get it, I'll just ask again.
I just made that up there, but.
Right, I don't understand. Why is it e to the ln y? It's left, right.
Well, okay, so this was more using the Ethan version of he suggested doing e. If you're going left, right, middle, you're going to go straight from here down to here.
Okay.
You could ignore that step right there. I just wanted to demonstrate that that's also a way to think about it. Both are perfectly valid reasons. The left, right, middle is really just kind of shortcutting this. But left, right, middle is kind of what we learned first, if you think about it.
And so the reason my mind went there is because I was thinking of like when you're in an equation and you're trying to get rid of like a sine, cosine, or tangent, you do like the inverse. So I was like, oh. So
yeah. Because like here, for a basic one, like if I said left, right, middle, 6 to the 5th equals x, right?
Yeah.
Left, right, middle. And that's exactly what that is. E to that mess equals y. That's left, right, middle. However, I'm going to erase this in a moment. I'm not leaving it here. Earlier, Ethan suggested we give everything a base of e. What base would I give things here? This is a base of 6. So I would say, okay, this is 6 to log base 6 of x equals 6 to the 5th. There's a log rule that says when these 6's match, basically this is x, it's whatever that is, equals the other piece. I don't care if you think about it this way or think about it this way. They're both very legitimate ways. Honestly, what I just showed you is probably the reason left, right, middle works. That's probably what you would hear someone say. Okay, I hopefully didn't erase that too soon there. Okay, B. Using the tangent line to the curve at x equals 1, find the number k such that the point 1.25 k is on the curve. Thoughts?
You plug 1.25 as y.
As what?
As y.
Not as y.
Oh, as x.
As x. Basically, guys, you're plugging 1.25 into this equation as x, and my equation then will equal our y value, which is what they're wanting us to find. They're wanting us to find k, but that's really just our y value. Okay, so if we think of this in terms of an x, y.
So why is your k a y value? Because like if it's
Because it's in the y spot of the ordered pair?
well, yeah, but like you're looking at it. If you're looking for that point, it's off to the side. It's like wouldn't you want? It's like wouldn't the y values be the same?
and the differences in the x values? Is that?
Well, there's a difference in both the x and the y values. The x is the difference from 1 to 1.25, and that has to be very close. The difference in the y values, that's what we've been finding the error on.
Okay, I guess it just looks different because like I was thinking of the distance between the like graph and then the tangent line.
Okay, yeah. Like this right here is your difference in your x values. This right here is your difference in your y values, or in this case, it's going to be your difference in your k value. Well, not the difference. I shouldn't say that. Never mind. Strike what I was. But that's your difference in the y values there. Okay. Okay, so I'm basically going to find my linear approximation at 1.25. So f of 1.25 is approximately equal to L of 1.25, which is 3 times 1.25 minus 1 plus 1. And essentially, that's going to equal k then. Let's see, 3 times 0.25 plus 1. 1.75. Now, C asks us to calculate the error of the approximation. In order to calculate the error of the approximation, we have to know our linear approximation. We also have to know the actual. Do we know the actual value at 1.25? In other words, approximately right there. Do we know that value? No. How do we find the actual value? Take 1.25, plug it into the original equation. So you have an option. You can plug it into the implicit form if you want, and then you have to solve for y, or we've already done that work, haven't we? And we can plug that in. So if I do, actually, whoops, this is finding f of 1.25. You're doing e to the 1.25 squared plus natural log of 1.25 minus 1. This is a handy dandy calculator thing, isn't it? And this is going to be our exact. Do I have this one written down? Did you get something? Did you get something beginning with 2? 2.19382 is what I have written down in my notes. Who knows if it's accurate? I have weird stuff in my notes today. Now, based on where I put the dot, is that possible? That is possible, right? Because it's something above 2. So that is possible there. Now, in order to do the error of the approximation, so we're going to do exact minus approximate. So what's my exact? That is the 2.19382 minus my approximate, which was 1.75. Or in other words, if you will, that was f of 1.25 minus L of 1.25 is what that really was. 0 point something. So I have 44381 written in my notes. Okay. Now, real quick, one thing, and it just said error of approximation here, but there are a couple of times in homework it asks for percent of error. I think that's the phrasing. But if you go back to the beginning of our notes, we had a formula to find percent of error. Huh?
We use that in physics.
Lab day.
Okay, so, probably no percent error. But in order to do percent error, that's when you're doing the exact minus approximate and then divide by exact, right? So in homework, you might have to do some physics. Is that a good way to say it? Okay, so in order to do your percent error, you're going to be doing the exact minus approximate divided by exact, and that'll give you a decimal, and you know then you would take the decimal and multiply by 100 if you need the percent, right? I lost my page. I have written down 20.23%. Is that right? Okay. I did not fill all the numbers in. I think you guys are smart enough to do that. Actually, I know you are. Okay.
I missed geometry.
4.5 homework for tomorrow.
I miss like algebra 2 and 3 out. I hate geometry.
Geometry was